In this video, we're going to continue our discussion of hierarchical linear modeling, now looking at the context in which we would use these models as well as the general modeling framework. So it's important to start by mentioning that regression is one of the most useful statistical tools that we have in our handbag. It is extraordinarily diverse, it's very flexible, and has a lot of different modifications that we can drop in depending on the situation we're trying to model. But in many social situations, social science situations, we're looking at data that violate core assumptions of regression. And one very often violated assumption is the assumption of independence. Now, what does this assumption of independence mean, or the violation of it mean? Well, if we don't have independence, sometimes we get these clusters within our data. That is, maybe a group of individuals who are grouped together in a way that's not accounted for by the model. Sometimes this can be in a case where I'm trying to gather a bunch of students, and maybe some of the students are in the same classroom. And so that classroom is the cluster. Students are nested within a classroom, is one way we could say that. Or maybe I'm trying to get a whole bunch of employees or salespeople who are at a variety of different companies, but some of the salespeople are at the same company. And so in that particular case, these individuals might be clustered together from that perspective. Uh, in these situations, the clustering can't always be avoided. In fact, many times it can't be avoided at all. So if I am looking at studying students, it would be very difficult to study students who aren't in different classes. Because if I wanted to stay in the same class, those students, I'd be very limited in terms of my sample size. Maybe what, 30 students, 40 students? Maybe if I got a massive lecture class, 200 students. But even that's a very, very, very reduced sample size to the possibility of having many, many students within my sample. So in this particular case, clustering really can't be avoided. I need to get more students for my study, so I'm going to have to go outside of that single class. But then again, this clustering is introduced where students are clustered or nested within their classes. If mishandled, this clustering can cause some serious problems. It can affect our parameter estimation, and most importantly, it can affect our significance testing in a pretty drastic way. So we'll talk about a couple of these in a second, but first, let's talk about some possible situations. So consider a situation where we're studying motivation of 315 employees in 7 different departments, and these employees are clustered in their different departments. Or we might say employee is nested within department. For another situation, we might be studying the performance of a variety of different stores, 18 stores, in different cities. So the stores might be clustered by city. Or we might be studying job aptitude over time. And this one's an interesting one. This will pop up throughout our lecture set on HLM, though it won't be a major focus for us. That when we're studying job aptitude over time, or really anything over time, time can be a portion of our nesting or one of the structures of our nesting that we can look at. In this particular case, consider somebody taking pre and post test. What we would look at is the pre test data and the post test data are both nested within the individual who took them. That is, they are influenced by the same individual who took both of them together. And consider some possible research questions that may fall out of this. I may look at employee motivation as the outcome as it relates to department head characteristics. So I might have the department chair, an attribute of the cluster, um, as part of the model where I'm looking at employee motivation. And I mentioned first and second level here. We'll discuss this later on, but just consider that the independent variables part of the cluster and the dependent variables part of the employee. So I can look at things that are both employee traits and department traits. So employee traits and cluster traits. I could look at store performance as it relates to store pricing and just account for the fact that in different cities, I might have different trends going on. I could also look at individual aptitude, say before and after a training, if I were studying them over time to see to what degree did the individual help individuals, excuse me, did the training help individuals' job aptitude. Now, it's important as we talk about this that we address the elephant in the room, and that is that sometimes, especially when we deal with a new or complicated method, we're very tempted to say, yeah, but I just did it the easy way and it ran in software and isn't that okay? And that's a lot of people's gut reaction to complicated situations. Maybe a statistical assumption was violated, normality, and sometimes we just try to ignore it. So it's important to realize what the effect of doing that can be. So let's talk about what happens when you ignore this structure. So let's say we're looking at the employees within the department and we're looking at the department head characteristics. And so, how I would include department head characteristics if I ignore the structure, there's two ways. One is I could just, for every employee, I could write their department head characteristics. So, employee one, this is all their stuff, and their department head was a jerk. Or employee one, this is all their stuff, and the department head was really nice. And so, I include the group, that is the department level variables at the individual level. And sometimes this is called the atomistic fallacy. Here, the type 1 error rate can be raised from 0.05 to as high as 0.17 with a relatively small clustering effect. So what does this mean? This means that when I'm comparing to my 0.05 cutoff, and I think that I'm only making an error 5% of the time, actually, even comparing to that 0.05 cutoff, it turns out I'm actually making an error 17% of the time, as high as 17% of the time, even if the cluster effect is relatively minor. Now, if the cluster effect is major, I'm still comparing to the 0.05 cutoff for all my p-values, but in that case, my error can be as high as 70% with a large clustering effect. So my error rate is drastically raised. And again, it looks like, because all my p-values are being compared to 0.05, that this isn't an error, but in fact, my error rate is drastically different, drastically higher specifically. All right, so let's look at this the other way. Instead of looking at individual level outcomes, let's put everything at the group level, which has been dubbed the ecological fallacy. Um, for this, what ends up happening is because I'm no longer studying individuals, I'm now studying groups, I have a much smaller sample size and my statistical power is reduced, potentially drastically. On the other hand, if you had to pick one of these, this one is probably the more conservative approach of the two, so this would be the one to pick. We don't have to pick, that's why we have this lecture set. But if you did have to pick one, then this would be the more conservative of the approaches, um, which could be good or bad depending on the situation. But what does type 1 error rate increase really mean, and what does statistical power reducing really mean? But in essence, this is what they mean. For the first one, in essence, it'll leave you feeling much more confident than you should be. You'll feel much more confident about your results than you should be. You'll think things are very, very statistically significant when maybe they're marginal, or you'll think things are pretty statistically significant when maybe they aren't at all. So you're going to feel much more confident in your results than potentially you should be, and you're much, much more likely to find a statistically significant effect than you really should be. A lot of your statistically significant effects, if you did it the first way, probably aren't going to be statistically significant if you did it accurately, especially for your level 2 variables. If you do the second one and make all of your level 1 variables, all of your individual level variables treated at the group level, you're going to be feeling way less confident than you should be. That is, you're not going to be sure if there's an effect, even though maybe you should be if you would have analyzed the data appropriately. So ultimately, if you just run it and you run it using one of these two methods, treating the group at the individual level or the individuals, grouping them together, you're going to be left making a mistake, either feeling way more confident than you should about your results or way less confident than you should. So, how do you do it right? Well, the right way or the right level of confidence is called hierarchical linear modeling. It's a really broad classification of models, and we're not going to go into the complete breadth of it. We'll mention many extensions at the end of this lecture set that account for this nested or clustered data structure. Now, it's important to realize that this approach is actually called many different things. Sometimes you'll hear it called multi level linear modeling. This is what our Tabnachik and Fidel book call it, is multi-level linear modeling. And their explanation for why they do that is actually quite funny. So check it out if you haven't. Mixed models and random effects models is something this is called. Conditional models, you'll hear this called sometimes. Individual level models, you'll hear this called sometimes. There's a lot of different things that this is called depending on the fields that it's in, and realize all of these are ultimately referencing the same concept, and that is a way of dealing with these groups potentially that we have our individuals clustered into. Of course, these can do many more things than just deal with that. Again, we can look at data over time, which we normally wouldn't think of as being in groups. So this has a much broader usage. Um, and again, lots and lots of extensions that we won't have time to go into today. All right, so let's talk about some model concepts. And I've been mentioning this, but it's kind of time to define these a little bit more formally. So in the model, as we talk about hierarchical linear modeling, or HLM, we're going to be discussing levels. And when I say a level, I usually am going to have a number associated with it, level 1 or level 2 or level 3. The lower numbers are going to represent a more specific and smaller unit. So think people. And the larger numbers are going to represent a more broad or general, larger unit. So think company. So when I say level 1, that'll tend to be people. Level 2 tend to be maybe department or company, etc. So let's look at a couple examples. We might have person nested within department. And in that particular case, person would be level 1, and they're grouped inside of the departments, clustered in the departments, nested within the departments. Department would be level 2. I might have students nested within school, nested within district. And so this brings up an important point that I'll often talk about level 1 and 2, and all of our models today are going to be 2-level models in this lecture set. But the HLM method is much broader than this. We can easily have 3 levels implemented if we wanted to. So we could have student within school, within district. And then we could have time within student or time within person. And it's important to realize that time is going to be a level 1 variable. The responses at pre, post, and follow up are grouped within the person who made those responses, first and foremost. Often in a social situation, you'll see person as the lowest level, especially when we're looking at clustering by company or department. But if you're dealing with time, time is always going to be the lowest level. So if we have time in there, really time is almost always 99.9% of the time going to be the lowest level in our model. All right, so talking about these examples, I'm going to be using individual or person for the level 1, and group or company for the level 2. So I might have company, employee, individual versus group. And I'm going to do this without loss of generality, W log. Just what I mean by that is by saying I get that not all level 1s are necessarily people, and not all level 2s are necessarily groups or companies. This is done to help you understand the concept, but all of the explanations regarding this are going to be applicable to whatever your level 1 and level 2 classifications are. So we'll use individuals and groups, or again, employees and companies, and not really worry about the fact that not every level 1 is an employee and not every level 2 is a company. The interesting thing about modeling in hierarchical linear modeling is that because the group may affect the individuals, we have to account for this in the model. And what I mean by that is that within hierarchical modeling, the company effects might impact the individual effects. So the company might have something that impacts the individual. And we have to account for the fact that the company impacts the individual in the model, and that the individual has its own equation and the company might have its own equation. And this is the solution to how we can account for company impact on individuals, is that we have a series of related models to each other. Now, you may see these models written in different forms. Based on my background and training, I tend to prefer the hierarchical form, which is very common in HLM, and it really clarifies what level each particular thing is associated with. Now, hierarchical form is actually a little bit more restrictive. There are some cases when we're thinking through this that by looking at it in the hierarchical form, we run into problems conceptualizing the idea. Um, but I find the hierarchical form to be a pretty good default in terms of visualizing these types of systems of models. The second way is the combined form, which is very common in mixed models, and really it just combines all of the equations in a very, very, very long equation, um, which is, again, from my perspective, sometimes less interpretable, but certainly more flexible conceptually. So it really depends on what we're working on. My default and what we're going to implement in this lecture set is the hierarchical form, though we will discuss and demonstrate the combined forms. And it's important to realize that both of these are mathematically quote unquote right. That is, it's not really the case that one of these is the only way to do it. Far from it, both of these represent mathematically the exact same concepts. So we don't really have to pick one or the other. We do when we're writing out the equations for the models, but don't feel like that because you wrote it in a different form, as long as it represents the same thing, that you're going to get different results. It's just a representation to help and aid interpretation. All right. So the general model for level one, and remember this is the individual level, is going to have a very similar feel to regression. So if you remember regression, y equals beta 0 plus beta 1x plus epsilon, this is exactly that. Hey, this feels all nice and familiar. But what we're going to end up doing is, again, letting each company have its own relationship or have its own equation as it relates to the individual connected to the outcome. So, for a hypothetical case that we can kind of talk through here, let's say we're going to look at individual level skill and that skill's relationship to that individual's salary. Seems like a reasonable thing to study. And I might want to account for the fact that different companies may have a different base pay, that beta 0. Maybe different companies have a different base pay than each other. And maybe as an individual skill increases and they get salary bonuses and stuff by being more talented, some companies compensate those individuals differently. So I have individual and the skill relationship with salary. That's the individual level model. But now I want to account for the fact that individuals are nested within these companies, and each company might have its own contributing factor within this model. What I'm going to do to add company to this model is I'm going to add another subscript to each one of these variables. And that's going to represent the nesting structure in the hierarchical data. That is, that individuals are nested within the company in which they work. The subscript I'm going to add is a sub j, and this sub j is going to represent the company. And again, I have my outcome, salary, nested within company. I have my x independent variable, skill, nested within company. But the beta 0, the base salary, that is the salary with 0 skill, That might change depending on what the company is. And that's what the additional subscriptive J represents, is that my base pay may change depending on company. Similarly, my beta 1, that is the relationship between skill and salary, or the salary bump I get when my skill goes up, different companies might give me different salary bumps when my skill goes up. So that's why beta 1 has a little sub J next to it. All right, so now that we have this, it's important to realize that we don't just want to add the fact that, hey, company could be related. We want to systematize that a little bit more. So each of these beta values are going to have their own models in a hierarchical linear modeling structure. Beta 0 sub j is going to have its own model. Those y looking things in the beta 0 sub j and beta 1 sub j model are called gammas. They're a Greek letter. And ultimately, those gammas are going to represent what we used to consider our betas. The interpretation is going to be the same, and we'll get there in a bit. And then we have W and U, and all of these things have their own interpretations. We're going to go into the interpretations in a second. But this is the broad structure of what a hierarchical linear model looks like. We tend to break this up in terms of a level 1 and level 2 model. The top equation with the y equals is typically considered a level 1 model and represents the model from the perspective of the employee. The second set of two equations are called the level 2 model or the level 2 models, and those represent how the company impacts the employee. So again, level 1's the employee's relationship of skill versus salary. Level 2 is the company's impact on that relationship. So maybe company characteristics. For a company characteristic, maybe the company is private versus public. Maybe that has an impact on the base pay salary or on the way in which skill is compensated. And maybe overall company has an effect too. And as you can see, interpretations are going to get a bit tricky here. So this is going to be something that we're going to need some practice working through. We're going to take some time working through as these interpretations. But this is the general model that we're going to focus on within this lecture set for hierarchical linear modeling. All right, well, in this video, we talked about some context and talked about the general model. We're now going to move on to some of the concepts and interpretations in the next video.